in the final breath of the universe we know. A colossal wall of stars called Andromeda drifts slowly toward the Milky Way like a destined visitor. No sound. No warning. Only the promise of a cosmic reunion that may remake our entire night sky. If you've ever wondered what truly happens when two galaxies touch, let your heart open and feel the scale of it. Share your thoughts in the comments. Could this be our ending or the beginning of something new? And now we step into the first question. What exactly will happen when Andromeda hits the Milky Way? What exactly happens when two entire galaxies fall in love and pass through each other like ghosts across billions of years, rather than like cars crashing on a highway in a single instant? Imagine looking up one distant night and seeing not a faint smudge in the constellation Andromeda, but a vast luminous river of stars stretching across the whole sky, silently approaching our own pale band of the Milky Way. The question that whispers inside that vision is simple and terrifying at once. What will truly happen when those two rivers finally meet? At first, our human instincts picture impact and destruction. Explosions, fragments, chaos like metal twisting in a collision on a dark road. But a galaxy is almost entirely empty space. And that emptiness is the secret that turns horror into something strangely gentle and contemplative. Carl Sagan once reminded us that space is not only more vast than we imagine, it is more vast than we can imagine. Between one star and the next there is so much nothing that even when two galaxies overlap, almost no individual stars actually hit each other at all. When Andromeda falls into our Milky Way, their disks will interpenetrate like two swarms of fireflies drifting through the same summer field, each light aware only of the distant gravitational pull of the others. Neil deGrasse Tyson likes to say that if the sun were the size of a basketball, the nearest star would be another basketball thousands of kilometers away. Put two such star fields together, and you do not get a pile of broken spheres. You get two lattices of light weaving through one another. So the answer to the first fear is quiet. No. The collision will not slice our galaxy in half like a sword through paper. It will not rip every star from every orbit in a sudden blaze. Instead, gravity will play a long, slow piece of music, more like a symphony unfolding over 2 billion years than a single drumbeat. The arms of each spiral will stretch and warp. Tidal tails of stars will be drawn out like silver threads from a woven cloth. And the neat disks we know today will puff into a rounder cloud of random orbits. That leads to the second question in the mind of anyone watching this video with a quiet knot in the stomach. What about us? What about the sun and Earth? Will another star come roaring in and knock our world into the dark between galaxies? Here again, the numbers are on our side. Astrophysicists have simulated the future dance many times, and the chance that a star passes close enough to dramatically disturb our orbit is very small, perhaps less than 1 in 100. Our system is like a tiny boat on a huge ocean, and even during a storm, most boats are only lifted and lowered by the long, slow swell. What will change is the grand stage set around us, not necessarily the local lamp that warms our seas. As Andromeda draws nearer, its spiral arms will bloom in the sky like a second Milky Way facing our own. Then the two will twist together in forms no human artist has ever seen. James Jeans once wrote that the universe begins to look more like a great thought than a great machine. In the era of the merger, that thought will be painted directly across the heavens, a living demonstration that structure itself is temporary. And yet, amidst all this vast choreography, there will be true violence in places we cannot see directly. At the center of each galaxy waits a supermassive black hole, millions to hundreds of millions of times the mass of the Sun. As the galaxies entangle, stars and gas will be funneled toward those dark hearts, feeding them and making them flare as active galactic nuclei. For a time, each core may outshine all its surrounding stars combined, a lighthouse of high-energy radiation blazing in X-rays and ultraviolet light. Eventually, the two black holes themselves will spiral together in a tightening orbit, losing energy to gravitational waves that ripple through the fabric of space-time. Einstein predicted such waves more than a century ago, and today instruments like LIGO have already heard the whispers of smaller black holes colliding. But the union of these two giants will be on an entirely different scale. An explosion of gravity so intense that for a moment more power is radiated in those waves than from all the stars in the observable universe combined. And yet, for any beings watching with ordinary eyes, the sky may show nothing more than a slight change in the glimmer at the galactic core. So we have this paradoxical story, a collision that is gentle and quiet from the point of view of a planet, yet unimaginably violent in the hidden realm of warped space-time and infalling gas. I find something deeply calming in that contradiction, a reminder that not every great change is an instant catastrophe. Some are slow tides, reshaping coasts over ages, while the waves at our feet seem almost unchanged. Of course, there are risks, and a scientist's honesty demands that we speak of them too. As stars pass a little closer than usual to our Sun, the delicate cloud of comets in the outermost reaches of our system may be disturbed. Some of those icy bodies could be nudged inward, increasing the rate of impacts on planets like Earth. In the deep future, long after our time, the sky may glow with more frequent bright comets and perhaps the scars of their landings. But set beside the timescale of life on Earth, the timescale of this galactic drama is almost abstract. Before Andromeda truly arrives, the Sun itself will have grown hotter, the oceans may have boiled away, and our world as a home for life like ours will likely have already ended. The real question then is not whether the merger threatens us, but what it teaches us about impermanence, even at the largest scales we can imagine. To me, there is a kind of cosmic mindfulness hidden here. Galaxies too are born, grow, collide, and fade. The elegant spiral we call the Milky Way is not an eternal logo stamped on the universe. It is a passing pattern in a restless sea of matter and gravity. Andromeda is not an enemy coming to end our story, but a future partner with whom we will write a new chapter under a different sky. Astrophysicist Avi Loeb has noted that in the far future, when dark energy has pushed most other galaxies beyond our horizon, the merged remnant of the Milky Way and Andromeda may be almost the only great island of stars left in our observable universe. Imagine descendants of distant civilizations looking out then, seeing only their own single galaxy, and perhaps concluding that nothing else ever existed. We live in a special moment, early enough to still see the wider cosmic web, yet mature enough to understand where it is all headed. That is the deeper gift of this story for me. Not fear, but perspective. To know that even our galaxy will someday lose its name. Becoming part of a new, is less than double, is greater than more massive, elliptical system people, now like to nickname Milkomeda, is to be reminded how small our personal dramas are in comparison. Yet it does not make them meaningless. Rather, it frames them, like small, bright candles in a vast, dark hall. As you listen to this in the quiet of your room, perhaps with eyes half closed, letting the images drift through your mind like constellations floating by, I invite you to treat this future collision not as a threat, but as a meditation bell. A soft chime across billions of years saying, remember, nothing stays the same. Not continents, not species, not even galaxies. What will you do with your brief moment in this slowly changing universe? If these thoughts stir something in you, a sense of awe, a quiet shiver of curiosity, let that be part of the experiment too. You can support journeys like this simply by liking this video and subscribing to the channel, not as a mechanical gesture, but as a small decision to keep returning to the night sky together. And in the comments, I would love to hear your own reflections. When you imagine the Milky Way and Andromeda merging, do you feel fear, peace, or something in between? Because this is only the beginning of our exploration, the first breath in a long story, spanning 4 billion years of future history. To truly understand it, we now have to step closer to the core of the mystery and ask in detail the very question that opened our journey. What exactly will happen when Andromeda hits the Milky Way? What if the real danger in the coming galactic merger is not the clash of a trillion stars, but the quiet fate of one star and the fragile world that circles it? When people hear that Andromeda is falling toward the Milky Way, the first question is almost always the same. What will happen to Earth and the Sun? We imagine two vast pinwheels of light crashing together, flinging planets like sparks from grinding metal. We picture our orbit ripped apart, Earth flung into the cold void between galaxies, or hurled inward toward a raging star. The reality is stranger, slower, and in some ways more hauntingly beautiful. To understand that future, we have to remember just how empty a galaxy really is. If the Sun were the size of a small ball resting in the center of a great stadium, the nearest star would be another ball sitting in a stadium, many countries away. Between them stretches almost pure darkness, a silence so wide that even when two galaxies overlap, almost every star simply glides past every other star without a single direct collision. As the physicist John Wheeler liked to say, space tells matter how to move, and matter tells space how to curve. In the merger, it is the curvature of space itself that changes slowly, not the sudden smashing of suns together. So what about the orbit of Earth? When Andromeda and the Milky Way first begin their slow interpenetration, the gravitational field around our Sun will start to feel a very gentle reshaping, like a tiny boat rising and falling on swells from a distant storm. The Sun will continue to circle the common center of the two galaxies, but its path may become more elongated, tilted slightly out of the original disk, or nudged outward into a wider galactic orbit. Most simulations suggest that while the large-scale trajectory of the Sun will change, the tight bond between the Sun and its planets remains almost untouched. Gravity close in is fierce. The pull of the Sun on Earth is enormously stronger than the subtle tug of distant stars. The probability that another star will pass close enough to violently disrupt our orbit is small, perhaps less than 1 chance in 100. Astrophysicist Martin Rees has warned that the universe is a dangerous place, but he also reminds us that most dangers are rare on human timescales. In that sense, our orbit is like a tight circle of dancers around a central flame, while the crowd around the hall shifts and surges very slowly in the background. Yet low probability does not mean zero, and somewhere in the long future a star may indeed wander a little too near our system. If it passes within a few light years, it is unlikely to tear the inner planets away, but it can disturb the delicate cloud of comets at the edge of the Sun's influence. Those distant bodies in the Oort cloud are barely held by solar gravity, and a small nudge can send some of them falling inward on long, icy trajectories. The consequence could be a season of heavier bombardment, more comets in the inner system, more brilliant tails in alien skies, and perhaps more impacts on any surviving worlds with oceans and atmospheres. In that sense, the merger does not so much strike us directly as rattle the shelves of the cosmic house we live in. But even that is not the main threat to Earth. Long before the dance of stars reaches its most tangled steps, the Sun itself will have been quietly changing. Stars do not burn forever at the same brightness. They age, thicken in the middle, and grow more intense as their fuel is rearranged inside. Our Sun is roughly halfway through its long life on the main sequence, slowly brightening by a few percent every 100 million years or so. At some point, perhaps a billion years from now, its extra heat will likely push Earth into a runaway greenhouse state. Oceans steaming away to the sky, continents baking under dense clouds of vapor and carbon. Carl Sagan reminded us that Earth is a pale blue dot, a mote of dust suspended in a sunbeam. In this future, it becomes a pale, scorched stone, the blue long since boiled off into space. By the time Andromeda's core looms large in our night sky, Earth as a living world is probably already gone. Life that began here will have either transformed utterly, moved on to other homes, or been erased by the slow mercy of stellar evolution. So when we ask whether Earth will be flung out of the solar system during the merger, the deeper truth is that the cosmological story and the biological story are out of sync. The galaxy takes its time, but the Sun needs no help from Andromeda to make Earth uninhabitable. Farther ahead still lies the most dramatic chapter in the Sun's own life. After roughly 10 billion years on the main sequence, its core will run low on easily fused hydrogen, and the star will respond by swelling into a red giant. The outer layers will puff outward until the Sun grows tens of times its present size, perhaps large enough to engulf Mercury and Venus entirely, and to roast Earth at a distance where rock begins to soften and seas are long-forgotten myths in the stone. As Brian Cox once put it, the universe will not notice when we are gone, yet every atom in us was forged in its fires. In the red giant phase, that forging continues. New shells of fusion building, heavier elements that will later be blown out into space as the star sheds its envelope and settles as a white dwarf. Can Earth survive that phase as a physical object? The answer is uncertain, and that uncertainty is itself a kind of poetry. Some calculations suggest that as the Sun loses mass through stellar winds, the orbits of its planets will expand slightly, perhaps just enough for Earth to slip outward rather than being swallowed. Other models say the drag of the swollen solar atmosphere could pull our world inward, melting it into the outer layers of the star. Either way, any trace of oceans or life or cities will be gone long before. When I think about this future, I do not feel despair so much as a strange clarity. We cling to the idea that safety lies in the familiar, in the orbit that never changes, in the Sun that rises in the same patch of sky every morning. Yet, the deeper lesson of astrophysics is that nothing holds its shape forever. Not galaxies. Not stars. Not even space itself. James Jeans wrote that the universe begins to look more like a great thought than a great machine. If that is true, then our brief existence on this world is a passing sentence in that great thought, a phrase that only makes sense because it will one day end. The merger of the Milky Way and Andromeda becomes, in that light, not a cosmic accident attacking us from outside, but a backdrop that reminds us to take ownership of our small moment. We may not be able to steer galaxies, but we can steer ourselves. We can decide to use the time before the oceans boil, before the stars shift, to understand the laws that govern all of this, and to treat our fragile world with a kind of tender seriousness. There is another layer to the question too. If our descendants become a spacefaring civilization, the merger might offer opportunities as well as threats. New stars born in the turbulent gas of colliding galaxies. New planetary systems rich in heavy elements. Shorter distances between some neighboring suns. A patient species could ride these changes like a surfer on very slow waves, hopping from system to system, carrying with them memories of the pale blue point where it all began. In that sense, the fate of Earth is not the fate of everything that grew from Earth. My own feeling is that this is the quiet invitation hidden in the science, to see that security does not lie in the promise that our orbit will never change, but in the growth of wisdom and compassion in the time, while it does not change. We are the only known species that can foresee both the death of its star and the merger of its galaxy, and still choose to love, to build, to learn. That choice gives meaning to a future in which our planet will eventually be no more than a warm memory in the cooled crust of a white dwarf or a lost pebble in interstellar space. If this slow journey through deep time brings you a sense of wonder, or even a gentle comfort as you drift towards sleep, you can help keep these cosmic stories alive by liking this video and subscribing to the channel. Not as a noisy gesture, but as a small act of alignment with curiosity, a way of saying that you too want to look honestly at our future under the stars. And in the quiet space of the comments, I would love to hear your own reflection. If you could stand safely beneath that future sky where Andromeda and the Milky Way intertwine, what would you feel for Earth and for the sun that once warmed it? What happens when the two darkest hearts of colliding galaxies finally find each other and fall into a last embrace? For a long time, Andromeda and the Milky Way dance at a distance, their starry arms stretching, twisting, tidal streams flowing like slow cosmic rivers. Yet hidden at the center of each graceful spiral is something that does not shine. A supermassive black hole, a well of gravity so deep that even light cannot climb out. One of them rests in our own core, Sagittarius, a star, a few million times the mass of the Sun. The other in Andromeda is far heavier, perhaps 100 million suns gathered into one invisible point. As the galaxies begin to merge, their stars move like a flock disturbed by a distant thunder. Orbits tilt, stretch, cross. Gas clouds collide and flare into new stars, blue and hot and short-lived. But the black holes remain patient in their separate nests, each wrapped in crowded swarms of stars and swirling gas. They do not rush together. They wait while gravity rearranges everything else. Einstein once said that imagination is more important than knowledge, because imagination embraces the whole world. To imagine this part of the story, we must picture not just objects moving through space, but space itself bending and ringing like a drum. As the two galactic cores sink closer, under their mutual pull, each black hole drags a wake of stars and dark matter behind it. This slows them down, the process astronomers call dynamical friction, until they are no longer just two seeds at opposite sides of a storm, but companions caught in the same gravitational well. Eventually they form a binary. Two supermassive black holes, orbiting a common center like titans, circling in silence. With every orbit, they stir the surrounding stars, flinging some outward, swallowing others. More importantly for the fabric of space-time itself, they begin to radiate gravitational waves. Kip Thorne has described gravitational waves as ripples in the curvature of space-time that travel at the speed of light. You can imagine them as concentric rings spreading across an invisible lake. Except this lake is four-dimensional, and the stones thrown into it are black holes, the size of solar systems. Far from the pair, a distant detector in some future civilization might feel those ripples as minute stretches and squeezes of distance, fractions of the width of an atom. To the black holes themselves, the waves are a kind of friction, carrying away orbital energy and angular momentum. The orbit shrinks, the period shortens. What once took millions of years becomes thousands, then centuries, then days, then seconds. In the final stage, the two horizons spiral around each other at a significant fraction of the speed of light, locked in an almost perfect dance of geometry and gravity. No light escapes from the holes themselves, yet the surrounding gas may glow fiercely, forming hot accretion flows that radiate X-rays and beams of particles. If the system ignites as a quasar, observers across the merged galaxy would see a single point flaring brighter than all the stars around it. Then comes the plunge. In a fraction of a second, the orbit tightens beyond any stable path, and the two horizons merge into one. The gravitational waves reach a peak, a sharp burst that carries away more energy than billions of supernovas would release over their entire lives. For an outside observer with suitable instruments, this moment would draw a beautiful pattern in their data, a chirp rising in frequency and amplitude, then fading into silence. For everyone else, there might be no visible sign at all, just the quiet continuation of a luminous core slowly settling down. After the merger, the new single black hole rings like a struck bell, its distorted horizon oscillating and then relaxing into a smooth shape. This ring-down phase is one of the purest predictions of general relativity, a kind of cosmic fingerprint of the theory itself. Saul Tucholsky once described black holes as the simplest macroscopic objects in the universe. They have no hair. In the end, all the messy details of the collision are lost behind the event horizon, leaving only mass, spin, and charge. Yet, there is another twist in this tale, one that sounds almost playful for such massive creatures. Because gravitational waves can carry momentum as well as energy, they can give the merged black hole a kick. If the two original holes had spins tilted in odd directions, or very different masses, the radiation pattern becomes lopsided. More waves are sent off in one direction than another, and by the law of action and reaction, the final black hole recoils in the opposite way. Simulations show that this gravitational recoil can reach thousands of kilometers per second. In extreme cases enough to launch the black hole out of the galactic center. Imagine that for a moment. The new heart of the merged galaxy kicked like a stone out of a sling, flying through the stellar bulge and into the halo. It would drag a cluster of stars with it, a compact little galaxy in miniature, leaving behind a strangely hollow core. Would it escape entirely, leaving the giant elliptical remnant with no central anchor? That depends on the depth of the gravitational well and the strength of the kick. In many realistic cases, the new black hole simply oscillates through the core, moving out, then falling back in. Over time, dynamical friction with surrounding stars and dark matter robs it of motion, letting it settle again at the center like a stone at the bottom of a pond. To me, there is a strange comfort in this image. Even after a violent union, even with a powerful recoil, gravity slowly heals the disturbance, returning the system to a new kind of equilibrium. Not the original order, but not pure chaos either. When I think about this, I hear an echo of John Wheeler's famous line that black holes have no hair. No matter how complicated the history, the final state is simple, elegant, stripped of detail. In a way, the merger of the two supermassive black holes at the centers of Milky Way and Andromeda is the emotional core of the whole galactic collision. Billions of stars will be shuffled like grains of sand in a slow tide. But these two objects carry the deep memory of both galaxies into a single future. There is a quiet lesson hiding here about identity and change, even at our human scale. We tend to think of the Milky Way as a fixed home, a great wheel of stars that simply is. Yet its very heart is destined to merge with another, to ring with gravitational music, to be kicked, to resettle. Our personal lives are filled with smaller versions of this story, collisions of choices and people and events that reshape who we are, leaving us simpler on the outside, but carrying complex hidden histories within. From the point of view of any beings who might live through that distant epoch, the merger of the two central black holes could be the greatest scientific spectacle imaginable. Their detectors would listen for the final chirp. Their telescopes would watch the changing core. Their theories would be tested against reality in the most extreme regime nature can provide. But from the point of view of an ordinary world orbiting an ordinary star somewhere in the halo, it might pass almost unnoticed. Just another phase of a slowly changing sky. That contrast between unimaginable power and everyday calm is part of what makes this topic so hypnotic for me. It invites us to breathe slowly, to stretch our sense of time, to let our worries shrink until they feel like ripples on a very small pond. Galaxies merge, black holes collide, space-time rings, and yet here we are, listening to these stories in the dark, perhaps on a phone screen before sleep. If this vision of two invisible giants spiraling together has stirred a little wonder in you, I invite you to keep traveling with me through these cosmic meditations. When you like this video and subscribe, you are not just pressing buttons, you are choosing to come back to the night sky, again and again. And in the comments, tell me what you feel when you picture those final orbits. Is it fear and awe, or a kind of deep cosmic peace? Because this story of merging black holes is not separate from the larger tale of Andromeda and the Milky Way. It is the heartbeat inside it. As we move on, we will lift our gaze from the dark core to the wider sky and ask how the rest of the galaxy responds when its central engine changes forever. What if the quietest object in your night sky is secretly screaming that an entire galaxy is falling toward us right now? High above the soft glow of cities, beyond the thin breath of Earth's air, Andromeda hangs like a small forgotten cloud to the naked eye. It looks harmless, almost shy, but every photon that reaches your eyes carries a message in its color. That message tells us Andromeda is not drifting away into the dark. It is rushing toward the Milky Way at about 110 kilometers per second. A silent approach, written in blue. Astronomers call this blue shift, the subtle tightening of light waves when a source moves toward us. The same way a siren rises in pitch as an ambulance comes closer. Starlight shifts toward shorter, bluer wavelengths when a galaxy falls in our direction. When we split Andromeda's light through a spectrograph, we see dark lines where atoms in its stars have absorbed specific colors, like fingerprints left on the spectrum. Those fingerprints are displaced slightly from where they should be in a resting lab on Earth, nudged toward the blue. From that tiny nudge, using the physics of the Doppler effect, we can calculate the speed of approach with astonishing precision. Edwin Hubble once remarked that the history of astronomy is a history of receding horizons, each new observation pushing our understanding further out. When he and those who came after him measured Andromeda, they discovered something that broke the pattern. Almost every distant galaxy shows a redshift because the universe is expanding. But Andromeda is different. Its light leans blue, meaning that against the grand outward flow of space itself, gravity has woven a private destiny between our two galaxies. How do we trust a number like 110 kilometers per second? A speed utterly beyond human intuition. The answer lies in repetition and refinement, in generations of telescopes turning toward the same faint smudge and reading the same pattern in its light. Different instruments, different teams, different years. Yet the same conclusion keeps returning like a tide. Andromeda is falling toward us, not as a threat for tomorrow, but as an appointment set roughly 4 billion years from now. As Neil deGrasse Tyson likes to say, the universe is under no obligation to make sense to you. Yet here, in the fine structure of a spectrum, it speaks with remarkable clarity. If the speed is the first secret, the second is what this motion will do to the sky above any future world that dares to look up. Imagine taking a time-lapse not over hours, but over millions of years. Every generation a new frame added to a cosmic film. At first, Andromeda is just a faint almond of light in the constellation that bears its name, something ancient astronomers once described as a little cloud. But as the aeons unwind, it grows, and grows, and grows. There will come an age when any nightwalker on a distant evolved Earth or some successor habitat will no longer see Andromeda as a smudge, but as a structured spiral. The dark lanes of dust will be visible to the unaided eye, threading through its glowing disk like veins in marble. Star-forming regions will appear as tiny blue embers scattered along its arms, each one a nursery of short-lived giants. The Milky Way itself will paint one luminous river across the sky, while Andromeda rises opposite it, a second river approaching slowly season by season. Brian Cox has said that the cosmos is not only stranger than we imagine, it is stranger than we can imagine. A sky hosting two colliding galaxies is a perfect illustration of that thought. As the dance advances, Gravity will pull on the outer stars of each galaxy the way the moon pulls on our oceans. Long tidal tails of stars will begin to stretch outward, forming ghostly arcs that curve across the void. From the surface of a world inside the Milky Way, those arcs may appear as new, faint bridges of starlight, curving between our familiar band and the broadening face of Andromeda. It will be as if the two galaxies are reaching out to hold hands across hundreds of thousands of light years. Then comes the first true overlap, when the disks interpenetrate and the sky becomes a layered tapestry of chaos and beauty. From one horizon to the other, you would see not a single Milky Way band, but a tangled weave of star clouds, luminous knots, and dark rifts of dust blocking out the light behind them. The familiar constellations that once guided sailors and storytellers will be erased, replaced by vistas for which human language has no names. Yet on the ground, for any creatures that still walk a planet, days will continue, seasons will turn, and the slow changes in the sky will be something you notice only when you compare the drawings of ancestors to the photographs of your age. Stephen Hawking reminded us that we are just an advanced breed of monkeys on a minor planet of a very average star. But we can understand the universe. To imagine this future sky is to exercise that understanding to its farthest horizon. We know that despite the apparent collision, almost no stars will strike each other, because the space between them is so vast. What will collide instead are the rivers of gas and dust, compressing into new waves of star formation. On the sky this will appear as sudden blooms of bright blue clusters and glowing nebulas sprayed across both galaxies. Cosmic fireworks stretched over millions of years. As the merger progresses through second and third passes, the elegant spiral arms that once defined each galaxy will be torn and rewoven. To an observer, the pattern will shift from two ordered pinwheels to a single enormous and increasingly rounded glow, a swelling central brightness, surrounded by a fog of scattered stars. Over further billions of years, that glow will settle into the shape astronomers call an elliptical galaxy. No more sharp disk, no more razor-thin lane of the Milky Way, but a more uniform dome of starlight surrounding every vantage point. In that far future, if any being stands beneath a dark sky inside the merged system that some playfully name Milkomeda, their view will be profoundly different from our own. The night will not have a single bright band but a more even sprinkling of stars in all directions, thickening toward the galactic center like the glow of a distant city. The young blue stars born in the fury of the merger will by then mostly be gone, leaving behind redder, older populations. The sky will look older, quieter, as if the galaxy has exhaled after a long tempest and settled into a contemplative age. And yet, all of this begins with a faint shift toward blue in the light of a smudge above our heads tonight. A tiny movement in wavelength, measured through glass and silicon, opens a window onto events that span the entire remaining lifetime of our star and beyond. This is the subtle magic of cosmology. From almost nothing in the data, we infer almost everything about our future sky. So when you hear that Andromeda is rushing toward us at 110 kilometers per second, do not imagine an impact in the human sense. Picture instead a slow tidal embrace, a dance in which the choreography is written by gravity and traced in light. Picture a night sky where two great rivers of stars move inexorably together until your descendants, if any still remain, will no longer speak of the Milky Way and Andromeda as separate things at all. And as you let that image settle, let one more question rise gently in your mind. When a galaxy that seems so small and harmless to your naked eye can reshape the entire future of our sky, what else in the quiet darkness above you is already in motion in ways you have not yet learned to see? Have you ever wondered why the most dramatic collision in the history of our galaxy moves so slowly that no single human eye would ever see it finish? We imagine crashes as sudden things, metal on metal, rock against rock, an instant of chaos and then silence. But when Andromeda falls toward the Milky Way, the universe chooses another tempo. A tempo stretched across billions of years. A tempo so chummed that even entire civilizations would rise and fall while the two galaxies barely lean a little closer. To understand why, we first need to feel how empty a galaxy really is. A star like our Sun is huge on the scale of planets. Yet between one star and the next, there is so much darkness that the Sun could shrink to a grain of sand and the nearest star would still sit several football fields away. Astrophysicists often say that a galaxy collision is more like two swarms of fireflies passing through a stadium than two solid objects hitting each other. Bright points drifting in a vast night, with almost no chance to touch. That is why two whole galactic disks can overlap without most stars ever meeting face to face. Gravity feels strong on the scale of galaxies, but the space between individual suns is an ocean of almost pure nothing. So Andromeda approaches at 110 kilometers each second, a speed that would wrap you around Earth in minutes. Yet because the distance is measured not in kilometers but in millions of years of light, the fall becomes a very long story. As the great cosmologist Martin Rees once explained, in essence, the universe can move with ferocious speed and still look frozen to creatures who live for only a few heartbeats of cosmic time. We are those creatures. We measure our lives in decades, our history in a few thousand years. The dance of galaxies ignores such tiny units. Yet slow does not mean simple. When Andromeda and the Milky Way finally meet, they will not simply stick together and stop. They will pass through each other, stretch, swing apart, and then fall back again. Imagine dropping a ball into a smooth bowl. It does not roll to the center and rest at once. It slides down one side, climbs the other, back and forth, each arc a little lower than before. The orbits of two massive galaxies behave in almost the same way. Each close passage robs a little orbital energy through countless tiny, gravitational tugs with stars and dark matter, a process astronomers call dynamical friction. Bit by bit, the grand orbit shrinks. The swings become shorter, until at last both cores settle into one common center. During moi lut kaien quan hao nu the, mut kuyentin tenung man lit, saira. Gravity does not pull equally on every part of a galaxy. It is always slightly stronger on the side, closer to the other galaxy, and slightly weaker on the far side. This difference is what we call a tidal force. You already feel a tiny version of it on Earth. The moon pulls a little harder on the near side of our oceans than on the far side. So the seas rise and fall like a slow breath. Now replace the moon with an entire galaxy and the oceans with rivers of stars. On the side of the Milky Way that faces Andromeda, stars and gas clouds feel a stronger pull toward that approaching giant. On the far side they feel less pull, so they lag behind. The result is stretching, a gentle at first and then dramatic elongation of the galactic disk. Streams of stars are drawn out like luminous silk, slipping from the edge of a spinning wheel. These are the tidal tails. But these tails do not simply point straight toward Andromeda and away from it. Both galaxies are rotating while they pull on each other. So the stars that are being stretched also continue to move along their original circular paths. Combine the inward pull with the sideways motion and the tails curve gracefully through space. Huge arcs that can span hundreds of thousands of light years. Computer simulations show these arcs twisting around the merging galaxies like slow spirals of smoke, fragile yet made of billions of suns. One leading astrophysicist once described such scenes as a ballet of gravity written in the language of patience and light. And it is hard to find better words. For me, this is where the story stops being only mechanics and begins to feel almost spiritual. We like to think of power as something sudden, an explosion, a flare, a single decisive event. Yet the universe quietly reminds us that the most profound transformations can be almost impossibly slow, sculpted by billions of tiny pulls, rather than one violent shove. The orbit that repeats like a ball in a bowl, losing a little energy each time, becomes a metaphor for change in our own lives. We swing between choices, between hopes and fears, and with every pass, we are nudged a little closer to some new center we cannot yet see. Look again at those tidal tails in your mind. Every star inside them used to circle calmly within its parent galaxy, part of a familiar disk, a known neighborhood. Now it is lifted up and stretched out into intergalactic space, set upon a long arc that may carry it far from its birthplace. Some tails will eventually fall back, raining stars into the remnant galaxy. Others may escape entirely, becoming lonely streams drifting through the darkness between islands of light. In the sky of a world orbiting one of those exiled suns, the merged galaxy might shine as a distant glowing cloud while their own star speeds on a separate path. There is a strange tenderness in this image. The pull that tears a galaxy open is the very same law that keeps planets in orbit and moons bound to worlds. A single rule of gravity writing both harmony and disruption. As another astronomer once summarized for students, gravity is not cruel or kind. It is simply persistent. Given enough time, persistence can turn two spirals into one great ellipsoid of stars, can draw out rivers of light where once there were only quiet disks. When I think about all this, I cannot help but feel a gentle humility. Our entire species has existed for less time than it takes our sun to make one orbit around the galactic center. A single lap in a race that will continue long after we are gone. On that scale, we will never witness a full galaxy collision from start to finish. We only get to understand it with our minds, never with our eyes. And yet, understanding is its own kind of participation. To sit under a night sky and know that every star is part of a vast slow dance, that our own galaxy is already falling toward another, is to feel woven into a story far greater than our brief biographies. There is also a quiet lesson hidden in the numbers. If galaxies can take billions of years to merge, then perhaps it is all right that our own changes are gradual, that progress in science, in society, in personal life, arrives not as a sudden collision, but as a series of gentle pulls and repeated orbits around our problems. Every time we return to the same question with a slightly better telescope or a slightly more open mind, we lose a little of our old ignorance and settle a little closer to the truth. Just as the ball in the bowl cannot help but move toward the center, a curious mind cannot help but move toward deeper understanding if it keeps rolling. So as you listen to this cosmic tale in the dark, maybe lying back with your eyes closed, letting the images drift past like slow clouds, I invite you to do something very human. Share what this slow collision makes you feel. Does it frighten you, calm you, or fill you with wonder? When you leave a comment, you are not just helping an algorithm. You are adding your small voice to a choir of minds trying to make sense of the same immense story. And if you choose to stay with this channel, to subscribe and return for more journeys like this, you are choosing to walk a little further along the spiral path of curiosity with me. Because the tale of galactic tides and billion-year orbits is only the beginning. We have asked why the merger is so slow, why stars barely touch, why tidal tales curve like drawn-out whispers of light. But the deeper question still waits for us in the darkness ahead. What exactly will happen when Andromeda finally hits the Milky Way? And what will it mean for every world circling every quiet star inside this vast and patient collision? What if every time galaxies collide, the universe is not destroying itself, but quietly planting a forest of newborn stars? When two great disks of starlight draw near each other in the dark, it is not the stars that meet first. It is the cold, unseen rivers of gas flowing between them. Vast clouds of hydrogen drift for hundreds of light years, subtle and almost empty by human standards, yet heavy enough for gravity to keep them in a slow cosmic embrace. As Andromeda and the Milky Way begin their long approach, these clouds feel the pull before our eyes ever could. They stretch, they compress, they shudder like lungs taking a deeper breath than ever before. When two such clouds meet head-on, they do not pass through each other like the stars do. They collide. They shock. They squeeze. And inside that squeeze, gravity suddenly has the upper hand. The gas cools and thickens. Eddies of turbulence fold in on themselves. Knots of matter grow denser until they can no longer resist their own weight. Each knot collapses further. The core grows hot. Atoms begin to fuse. And in the quiet heart of the collision, a star is born. Not one star, but thousands, tens of thousands. An entire nursery lit in a single cosmic sigh. Astronomers call this a starburst, a brief storm of creation where a galaxy forms stars at 10 or 100 times its usual rate. From far away, these newborns do not look like infants. They blaze like young blue giants, massive and impatient, burning their fuel in only a few million years. Blue light is the language of hot, heavy stars. So when a starburst ignites a galaxy, its spiral arms take on a youthful hue, patches of sapphire and electric white scattered through the dust. To an observer in another corner of the universe, a merging pair of galaxies can look as if someone has painted them with luminous blue fire. The irony is gentle and cruel at once. The brightest stars are the ones that live the shortest lives. They flare. They sculpt their surroundings with winds and radiation. And then they die in supernovae, seeding the gas with heavy elements that someday may become planets and people. The great astronomer Subramanian Chandrasekhar once reflected that in the final analysis, every star is the story of a delicate balance between gravity and pressure. In a starburst, that story is written faster, more urgently, as if the universe has turned a page and decided to speak in bold instead of whispering in thin ink. Yet even this drama on the stage of gas and starlight is only the surface of a deeper play. Beneath the glowing arms of both galaxies, beneath the visible stars and the churning clouds, lies an invisible scaffold, the halo of dark matter. It extends far beyond the shining disk, 10 times wider, holding everything in a gentle but relentless grip. Vera Rubin, whose work transformed our view of galaxies, once noted that without this unseen mass, the outer stars of a galaxy should fly off into space instead of circling calmly as they do. Her measurements whispered a quiet revolution. Most of the matter in a galaxy is not the part that glows. When Andromeda and the Milky Way fall toward each other, it is these dark halos that touch first. Long before any starburst flares, long before any spiral arm is torn and stretched, the halos have already interlaced like two ghosts embracing in the dark. Their combined gravity deepens the potential well in which both galaxies move, like two leaves being drawn together on the surface of a vast unseen whirlpool. The visible gas clouds merely follow the contours carved by this invisible sea. Most of the pull that drives the collision is not from the starlight we can photograph, but from the silent weight of dark matter. James Peebles once suggested that cosmic structure is really a story written first in dark matter, with ordinary matter merely tracing its outlines. In a merger, this becomes almost painfully clear. Where the dark halos overlap most strongly, the gravitational field becomes steeper. Gas streams fall inward. Shocks grow stronger, and the starburst brightens. If you imagine the galaxy as a great city of lights, then dark matter is the quiet bedrock beneath the streets. It does not sparkle. It does not advertise its presence. Yet every building stands where it does, because of that unseen foundation. The blue glare of newborn stars in a starburst is like fireworks erupting over that city. But the shape of the skyline was decided long before, in the era when dark halos were assembling from the early universe. To me, there is something deeply moving in this partnership between the seen and the unseen. The most dramatic lights in the sky owe their birth to a choreography directed by something we cannot yet touch, cannot bottle in a laboratory, cannot even describe fully with our equations. We infer it from motion, from the way galaxies spin, from the bending of light in gravitational lenses, like watching grass move and guessing at the wind. In the quiet of the night, when we imagine our descendants looking up during the Andromeda encounter, perhaps they will see an arc of blue star forming regions stretching across the sky, like a river of luminous pollen drifting through the darkness. They may know that each glowing patch is the grave and cradle of countless worlds, and that somewhere behind that beauty, an invisible halo is still guiding the flow. Michio Kaku once remarked that we are the dreams that matter dreams for itself. And here the dream grows deeper, because even the dreamer is mostly dark matter whose face we have never seen. There is a lesson tucked inside this distant collision, one that reaches gently into our human lives. Creation often begins with compression, with pressure, with disturbance. Gas clouds must be squeezed before they can ignite into stars. Galaxies must collide before they can bloom in blue. In our own stories, the moments that feel like impact and chaos may be the very regions where new light will one day appear. And just as dark matter shapes the fate of galaxies without ever shining, so too the quiet, invisible choices and kindnesses in a life may carry far more weight than the bright episodes that everyone can see. From a scientific view, the starburst and the dark halo are data points, equations, simulations running on supercomputers. From a more contemplative view, they are metaphors written in starlight. The universe is telling us that light and darkness are not enemies, but partners in a larger design. That violence in the cosmos often hides a slow, patient creativity, and that what we do not see can still hold everything together. If this slow journey through starbirth and dark matter keeps you company tonight, if the image of blue galaxies blooming from invisible hands soothes your thoughts, you can gently let the algorithm know with a like and a small subscription click. It is a quiet way of saying to the cosmos that you wish to keep listening, to keep learning, to keep drifting along these rivers of time and light. Leave a comment with how you imagine the sky will look when the starburst of our future galaxy begins. Because somewhere far ahead, under a different firmament, minds very much like ours may be asking the same question, while new suns are born above them. What if the calm path of our sun through the galaxy is only a temporary illusion? Imagine every star you see in the night sky riding on an invisible river, orbiting peacefully around the galactic center for billions of years. And then one day that river turns rough, twisted by the gravity of another, approaching galaxy. Astronomers tell us that when the Milky Way and Andromeda begin their slow dance, the orbits of countless stars will be gently but relentlessly rearranged. Paths that were once smooth circles will stretch into long ellipses. Planes that were once aligned in a thin disk will tilt and warp, until the elegant spiral is no longer a tidy pattern but a three-dimensional cloud of wandering suns. As the physicist Martin Rees once reflected, on galactic scales, even small gravitational nudges can rewrite the architecture of entire systems. From far away, the merger will look like two shining swirls of light slowly melting into one another. From inside, it will feel more subtle, like a long meditation in which nothing seems to move in a single lifetime, yet everything transforms over eons. Each star is a pilgrim, each orbit a mantra repeated again and again around the galactic center. When Andromeda's gravity begins to pull on the Milky Way, those mantras are disturbed. The music goes off-key, and the disk thickens into something puffier and more chaotic. Spiral arms, which depend on billions of stars marching together in almost circular orbits, will slowly dissolve, as if someone had blown on a ring of smoke and turned it into a hazy cloud. On their own, these changes would already be fascinating, but for fragile creatures living on tiny planets, there is another story woven into this dance. Around our sun, far beyond the outer planets, lies a ghostly sphere of icy bodies called the Oort cloud. Billions of frozen relics from the birth of the solar system drift there, barely held by the sun's weak gravity at that distance. Under normal galactic conditions, a few of these fragments are bumped inward every million years or so, becoming the long-period comets that occasionally grace our skies. But in a merger, the environment changes. As stellar orbits are scrambled, other stars will pass a little closer to us than before, maybe within a few light years. That is still unimaginably distant in human terms, yet close enough for their gravity to reach into our Oort cloud and stir it like a spoon in a bowl of dark water. Some comets will be nudged outward, lost forever to interstellar space. Others will be nudged inward, their slow orbits bent so that they fall toward the inner solar system in great numbers. The serene black between the planets may then become a busier highway of icy visitors. Carl Sagan liked to remind us that comets are both messengers and destroyers. They may have delivered part of Earth's water, perhaps some of the organic molecules that helped life begin. Yet a single large impact can erase entire branches of the evolutionary tree. During a galactic merger, the dice are rolled more often. More comets means more chances for oceans to be seeded on some worlds and more chances for oceans to boil on others. For a civilization aware of this, the sky would no longer be just beautiful. It would be a reminder that the calm we enjoy is borrowed, not guaranteed. There is another kind of storm that awakens when galaxies collide. A storm of light itself. As gas clouds crash and compress, they ignite waves of star formation, birthing swarms of short-lived massive stars that shine fiercely and die young as supernovae. In the quiet spiral we live in now, supernovae are rare fireworks. In a merging system, they can become a regular drumbeat echoing through the galactic night. A supernova far away is harmless spectacle, a brilliant point that briefly rivals the light of a whole galaxy. But if one goes off within a few dozen light-years of a life-bearing planet, its high-energy radiation can peel away protective layers of atmosphere, especially the delicate ozone that shields the surface from ultraviolet light. Some studies suggest that mass extinctions in Earth's history might be linked to nearby stellar explosions. As astrophysicist Brian Fields has put it, the galaxy can occasionally reach out and touch the biosphere with a violent hand. In a merger, that hand may reach more often in certain neighborhoods. Not every region will share the same risk. Areas near intense star-forming regions, where massive stars are born and die in rapid succession, will become harsher environments for life. The inner parts of the new galaxy, rich in gas and crowded with stars, may experience a temporary blaze of high-energy radiation. Meanwhile, more distant halos, where stars are sparse and gas is thin, could remain relatively tranquil. If a civilization were able to travel between stars, it might choose to migrate outward, away from the violent heart of the merger and into quieter outskirts. The cosmos would become not only a subject of study, but a landscape of choices. Some valleys dangerous, some comparatively safe. When I imagine this future, I do not see only catastrophe. I see a test of awareness, humility, and foresight. Neil deGrasse Tyson once remarked that the universe is under no obligation to make sense to us, yet we insist on trying to understand it. In the context of a galactic merger, understanding becomes more than curiosity. It becomes a tool of survival. A species that can map stellar orbits, track dangerous supernova candidates, and foresee waves of comets has a chance to adapt, to shield its worlds, or to move on when the neighborhood grows hostile. There is a quiet lesson hidden here for us, even though the real merger is billions of years away. We live in a time when our sky still appears calm, our constellations stable, our sun's path around the galaxy almost perfectly circular. Yet the physics that will one day stir orbits, rattle the Oort cloud, and raise supernova storms already exists. The universe is not static, not for galaxies, not for stars, not for planets, not for us. So what do we do with this knowledge? First, we can allow it to soften our arrogance. Our civilization feels large on Earth, yet it is as small as a film of dew on a grain of sand when measured against the tides of a galaxy. Second, we can let it deepen our gratitude. The stable climate, the rare impacts, the absence of nearby supernovae in this epoch, All of these are conditions we did not earn, but which allow us to tell these stories at all. Third, we can treat curiosity as a responsibility, not a luxury. The more we understand the cosmos, the better prepared any descendants of ours will be when the calm river of stars becomes rough again. If you feel a quiet shiver listening to this, that is natural. It is the mind recognizing that the ground beneath our feet extends far beyond Earth, out through the planets, through the Oort cloud, through the spiral arms, and into the great encounter still to come. If journeys like this help you see the night sky with new eyes, consider leaving a like for this video, or subscribing so you can drift with me through more of these cosmic meditations. Your comments are like small lights in this vast darkness. I read them as carefully as astronomers read starlight. Tell me, in a galaxy that one day will shake our sun's orbit, stir our comets, and multiply the thunder of supernovae, what would you choose to protect? And what would you be willing to leave behind? As we continue, we will follow those disturbed orbits more closely, tracing how a single tug of gravity can turn a calm stellar path into a long wandering ellipse, and how that subtle change ripples outward through planets, comets, and the fragile possibility of life itself. What if the most powerful break in the universe is not a wall or a rope, but the soft, invisible pull of billions of tiny stars, slowing the fall of a galactic heart? When astronomers speak of dynamical friction, they are giving a poetic name to a simple but profound idea: that great things are tamed by the whispers of the many. Imagine the core of a galaxy as a luminous ship sailing through a sea of lesser stars, gas, and dark matter. As it plows forward, its gravity gathers a wake behind it, a crowd of stars slightly pulled off their former paths. That crowded wake tugs back on the core, stealing a little of its motion with every passing million years. Subramanian Chandrasekhar, the physicist who first described this process in detail, once said that gravity is the architect of the large-scale universe. Dynamical friction is one of the finest tools in that architecture, a cosmic brake pedal pressed by uncountable small feet. Now picture two spiral galaxies on a slow collision course, like two vast cities of light drawn together by a promise older than their stars. At first they glide past each other, tidal arms flung outward, but their bright cores keep most of their speed. Without some way to lose that energy, they would simply swing past and drift apart again into the dark. Dynamical friction is what prevents that lonely ending. Each time a dense galactic core dives through the swarm of stars in the other galaxy, it leaves behind a wake, and that wake pulls backward like the drag of water on a boat hull. Little stars, each almost powerless alone, together slow giants of hundreds of billions of suns. As the cores lose energy, they sink deeper toward the problem, shared center of the merging system. Pass after pass, the orbits shrink. The dance tightens, until at last the two cores settle into a single luminous heart inside a new galaxy. If you could watch this from within one of those galaxies, the change would be slow and hypnotic. Your own star would feel only the faintest change in its path. But above you, the sky would evolve from an ordered spiral into a tangled river of starlight. In that river, the same gravitational caress that slows the cores also stirs the outer suburbs of each system. Orbits that were once almost circular become stretched and twisted, like musical notes bent by a patient hand. Every small change in a star path is a new question asked of its planets. Here is where the story of dynamical friction meets the story of rogue planets. When two galaxies merge, close encounters between stars become more likely. Not collisions, but near misses where gravity speaks loudly for a moment. In a peaceful galaxy, a planetary system is like a family walking a quiet path together. The star in front, the planets following in obedient ellipses. Now imagine another family passing nearby in the dark. Another star with its own retinue. They do not touch. Yet their gravitational glances can be enough to knock one of the children off the trail. A planet that once circled its parent star can be flung outward into the interstellar night, still warm inside from ancient formation heat, but cut off from the comforting sunrise it once knew. This is a rogue planet, a world without a sun. Some astronomers suspect that there may already be as many rogue planets in our galaxy as there are stars. During a major merger, that number may increase dramatically. James Binney, a leading expert in galactic dynamics, has often emphasized that violent relaxation during mergers scatters orbits in every direction. In that scattering, some planets are inevitably given just enough extra speed to escape their stellar prisons. They drift into the dark like embers blown from a dying fire. Others do not simply escape. They are traded. A passing star can slow a planet just enough that its old parent loses its grip, and the newcomer becomes the new center of its orbit. In this way, a merger is not only a collision of galaxies but a quiet reshuffling of homes for countless worlds. Carl Sagan reminded us that we are star stuff contemplating the stars. Extend that thought a little, and you might say we are also orbital stuff contemplating the fragility of orbits. The path that keeps Earth at a gentle distance from the Sun is not guaranteed for all time. It is a balance of energies that could in principle be disturbed by a close encounter millions or billions of years from now. For us, the risk is tiny. Yet, the concept itself is humbling. In the grand era of mergers, the universe may be constantly righting and erasing such delicate balances. Think of a rogue planet set loose during the embrace of two spirals. At first, it still carries an invisible memory of its lost sun, its frozen continents, its buried oceans. As it travels through thickening star fields, it may pass near new suns, each flyby a chance for capture. Sometimes the geometry is wrong, and it continues on into the dark. Sometimes everything aligns just so, and the planet falls into a broad new orbit around a stranger star. If that new orbit passes through a region where warmth and light are gentle enough, a dead world could in principle wake again. The merger that once tore it from its cradle then becomes the author of its second sunrise. From a scientific point of view, the equations are clear. Dynamical friction arises from the cumulative gravitational tugs of many lighter bodies on a massive one moving through them, and the probability of planet ejection or capture can be estimated from 3 body interactions and the statistics of close passages. From a human point of view, though, there is something almost spiritual in the image of countless faint stars slowing a galaxy, and in lonely planets wandering between suns. Sean Carroll likes to say that the universe is under no obligation to make sense to us. Yet here it has given us a story that is both mechanically precise and emotionally resonant. A story in which the smallest actors change the destiny of the largest structures. In a sense, dynamical friction is cosmic compassion made mathematical. The many give a little of their ordered motion so that the few massive can come to rest, so that chaos becomes structure. And rogue planets are the quiet reminder that even in a universe governed by strict laws, Trajectories can be broken, homes can be lost, and new homes can sometimes be found. While galaxies merge and cores spiral inward, there are always stories playing out on the scale of single worlds. Stories of exile, capture, and rebirth. As you listen to this in the dark, perhaps with eyes half closed, imagine our own Milky Way beginning that long, slow waltz with Andromeda. Far from the glowing centers, in the quiet outskirts where our sun now drifts, dynamical friction will be at work like a distant tide. Somewhere out there, other planetary systems will feel stronger echoes of that tide, and a few of their planets will be set free or claimed by new stars. The same gravitational law that keeps you grounded on Earth will be writing new maps for entire worlds. So, when we ask how dynamical friction helps two galaxies stick together, or why mergers give birth to armies of rogue planets, we are really asking how change flows through the universe. Not in sudden explosions, but in slow, persistent drifts, in tiny tugs repeated over ages beyond our imagination. And perhaps, as you drift toward sleep, you can hold one last question in mind. If even galaxies can be slowed by the murmurs of small stars, and planets can lose and find suns in the shuffle of a merger, then what does that say about the fragility and the possibility of our own place in this vast, changing night? What if the Milky Way you see as a soft river of light is actually a graveyard of galaxies that came before us? For billions of years, our home has not only been a quiet island of stars, but a patient predator in the dark. Astronomers have traced faint streams of stars wrapping around the sky, like ghostly ribbons left behind by smaller galaxies that ventured too close. The Sagittarius dwarf galaxy, for example, is being torn apart right now, its stars stretched into long arcs that encircle the Milky Way like the echoes of a forgotten orbit. Each stream is a memory, a fossilized path of a galaxy that once had its own center, its own sky, its own story. And yet, all of those stories are now being folded into ours. Andromeda has done the same. Deep imaging reveals delicate shells and loops of stars far beyond its bright core, scars of ancient mergers that happened long before humans appeared on Earth. Once, these were separate galaxies traveling alone through space. Now, their stars orbit a new master, their identities dissolved into a greater whole. In this sense, the coming collision between the Milky Way and Andromeda is not the beginning of violence, but simply the next chapter in a very old habit of growth through consumption. When you look up at the gentle band of the Milky Way on a clear night, you are not seeing a single untouched object. You are seeing a mosaic, the blended remains of many smaller systems that were pulled in, stripped of their stars and gas, and slowly digested by gravity. Our galaxy is both a home and a hunger, both cradle and cemetery. But neither the Milky Way nor Andromeda lives alone in the dark. They belong to a small family of galaxies known as the local group. Imagine a handful of cosmic islands drifting together in a sea that is otherwise pulling everything apart. There is our Milky Way, Andromeda, the smaller triangulum galaxy M33, and dozens of tiny dwarf companions fluttering around them like sparks around a fire. For most of cosmic history, these galaxies have circled one another slowly, their mutual gravity binding them into a loose dance, while the wider universe expands around them. On the largest scales, Space itself is stretching, carrying distant galaxies away from each other at ever-increasing speeds. Yet on the scale of the local group, gravity has already won the argument against expansion. The galaxies here are condemned to meet, to merge, to fuse their histories into something new. So what will happen to Triangulum in this slow-moving storm? Some simulations suggest that M33 may spiral into Andromeda first, feeding its mass and disturbing its structure even before our own encounter begins. In that picture, Andromeda arrives at the collision already swollen by the remains of a younger sibling. Other models hint that Triangulum might thread a more complex path, weaving between the two giants before finally being swallowed by the merged remnant. Either way, its fate seems clear. In the very long future, there will be no Milky Way, no Andromeda, no Triangulum. There will only be one enormous galaxy formed from them all. Within this future colossus, the dwarfs that now accompany our galaxies will likely be consumed as well. The Magellanic clouds around the Milky Way, the small satellites around Andromeda, all of them are slowly sinking deeper into the shared gravitational well. Over tens of billions of years, the local group will not be a group at all. It will be a single massive galaxy, a final city of stars surrounded by darkness. To understand why this fate is so sealed, we have to step back and ask how cosmic expansion and gravity share the stage. When the universe was young, matter was closer together. Small clumps could collapse under their own gravity before expansion tore them apart. These clumps became the first galaxies, each one wrapped in a large halo of dark matter whose invisible gravity anchored it in place. As time went on, galaxies fell toward each other, merged, and formed groups and clusters. Then something strange began to dominate the story. Observations of distant supernovae and the cosmic microwave background tell us that the expansion of the universe is accelerating, driven by what we call dark energy. On scales larger than a group or cluster, this acceleration is relentless. Galaxies far from us are receding faster and faster, so quickly that no gravitational pull we can muster will ever bring them back. Inside the local group, however, things are different. Our galaxies are close enough and massive enough that their mutual gravity already outweighs the stretching of space between them. It is as if they sit inside a small pocket carved out against the general flow of expansion. Within that pocket, the future is contraction, not separation. Outside it, everything else drifts away forever. This leads to a quietly dramatic consequence for the deep future. As dark energy continues to drive expansion, galaxies beyond the local group will move away so quickly that their light will be redshifted beyond our ability to detect. Given enough time, an observer living inside the merged galaxy of the far future will look out and see only their own island of stars. No grand web of galaxies, no evidence of a wider cosmic structure. The universe will appear small and self-contained, a single luminous city floating in infinite night. From our vantage point today, we are fortunate. We live at a time when we can still see millions of galaxies, still trace the large-scale structure of the cosmos, still detect the faint afterglow of the Big Bang itself. We can map the local group and watch Andromeda inch across the sky, knowing that our descendants, if they exist, will inherit a very different view. There is a quiet poetry in the way gravity and expansion divide the universe into two stories. Inside-bound structures like the local group, gravity wins, sculpting mergers, collisions, and the slow building of larger galaxies from smaller ones. Outside those structures, dark energy wins. Distance grows, light fades, and communication becomes impossible. In the end, every group becomes an island. Every island becomes a solitary world of stars. When you picture the future merged galaxy, perhaps called Milky, imagine not just its size but its loneliness. All the stories of the Milky Way, all the stories of Andromeda, of Triangulum, of every dwarf captured along the way, will be folded into one colossal archive of stars. Yet beyond its outer halo, there will be nothing visible, no other cities of light to compare with. The observable universe for those future astronomers will be the local group and nothing else. If intelligent beings still exist, then they may never know that the cosmos was once filled with galaxies, that there was a time when the sky was rich with clues about its origins. Without the evidence we have today, they might conclude that their single giant galaxy is all that has ever been. The memory of a vast and expanding universe would be buried in the light that has already passed by. For us, here and now, this knowledge carries a strange tenderness. We are part of a galaxy that has survived many small collisions, that will one day merge with its great neighbor, that belongs to a small family destined to become one body. We are children of cannibal galaxies, living in a brief era when the wider universe is still visible. So when you look up at the Milky Way, you might imagine the faint signatures of the galaxies it has already consumed. You might picture Andromeda on its slow approach, Triangulum perhaps circling in to join the gathering. You might feel the paradox of it all. A universe that is at once coming together in small pockets and falling apart on the grandest scales. And as you breathe with that image, drifting between science and silence, you may find a new question rising in you. If our galaxy is built from the remains of others, and destined to merge into something larger still, then what exactly will happen when Andromeda finally meets the Milky Way? What if the last thing the universe remembers of the Milky Way is not a bright spiral at all, but a quiet red ghost drifting in a darkened sky? For most of our lives, we imagine our galaxy as a graceful pinwheel of light, arms unfurling through space like a cosmic flower in bloom. Yet the story that awaits us is softer, rounder, stranger. Long after Andromeda has fallen into our arms and the two great disks have torn each other apart, there will be no spiral to speak of. Just a single vast sphere of stars that astronomers like to nickname Milkomeda, or Milkdromeda. In that distant age, the sky will not carry the skill, familiar river of the Milky Way stretching across the night. Instead, wherever a traveler looks, they will stand inside a rounded ocean of starlight, thicker toward the center, thinning gently outward. No elegant arms, no lanes of dust carving dark paths through glowing spirals. The galaxy will have settled into an almost featureless halo, a soft, luminous cloud of ancient suns drifting together in a single shared gravitation. The Milky Way as we know it will survive only in memory, encoded in the orbits of a few wandering clusters, in faint shells and ripples of stars that once belonged to separate disks. To the careful eye, those ripples will be like wrinkles on an old face, hints of a long life of collisions and transformations. But to most beings who might look up in that time, there will be only one great galaxy to name. Our spiral home will have been folded into something larger. Its distinct identity dissolved just as a single wave disappears when it merges with the sea. Inside this new sphere, the stars will be different from the ones we know now. Today, the Milky Way shines with a mixture of blue-white giants and quieter yellow suns like our own, sprinkled with countless faint red dwarfs too dim for the naked eye. In the future of Milkomeda, the bright giants will be mostly gone. Their lives burn hot and fast, ending in spectacular supernovae after only a few million or tens of millions of years. On the scale of a galaxy that is hardly more than a heartbeat. What will remain are the patient ones. The small red stars that sip their fuel instead of devouring it. Red dwarfs are so modest in mass that they can shine for hundreds of billions of years, longer than the universe has even existed so far. As time flows forward through tens of billions of years, then hundreds, the glow of Milkomeda will shift toward deeper and deeper shades of red. The bright white and blue light of youth will fade, leaving a galaxy lit mostly by tiny crimson embers scattered through the dark. If you could stand on a quiet world in that era, the night sky would feel both crowded and subdued. Crowded because you would live inside a more spherical swarm of stars, with luminous points surrounding you in all directions rather than along a single band. Subdued because each star would be faint, their combined light a gentle glow rather than a blazing river. It would be like walking through an ancient city after midnight, when the fires still burn but most windows have gone dark. Yet even the red dwarfs cannot burn forever. Given enough time, their deep reservoirs of hydrogen will finally run low. Their steady flames will shrink, cool, and go out. The larger stars will already have passed through their own endings. Many will have swollen into red giants, shed their outer layers into ghostly nebulae, and collapsed into hot white dwarfs no larger than Earth yet as massive as the Sun. Others, more massive still, will have died more violently as supernovae, leaving behind neutron stars and black holes. As tens of billions of years unfold within Milkomeda, these remnants will come to dominate the population of the galaxy. Imagine a future in which the starry sky is filled not chiefly with living suns, but with corpses that still remember how to glow. White dwarfs cooling slowly through shades of blue and red into blackness. Neutron stars spinning like cosmic lighthouses for a while, then falling silent. Black holes moving invisibly through the dark. Astronomers today describe the age we live in as the stelliferous era, the age of stars. In the timeline of the universe, this is the bright afternoon, the period when hydrogen still gathers into new suns, when galaxies are busy forming and merging. The future of Milkomeda points beyond this afternoon toward a long twilight, when the last big reservoirs of gas have been exhausted or blown out into intergalactic space. Star formation will slow to a trickle, then nearly stop. The galaxy will no longer replace the stars it loses, just as an old forest ceases to sprout new trees once the soil is spent. In that twilight, the universe enters what physicists sometimes call the degenerate era. The name does not mean corrupted, only that matter is dominated by degenerate objects. White dwarfs, neutron stars, black holes. In Milkomeda, these remnants will drift through a galaxy that grows ever quieter. Occasional close encounters between white dwarfs may light up as brief supernovae, adding a momentary flash to the darkening scene. Sometimes a star may wander too near the central supermassive black hole and be torn apart, briefly forming a bright disk of infalling gas before disappearing beyond the horizon. But these events will become rarer with each passing eon. Given even longer spans of time, the story deepens further. White dwarfs that once glowed white-hot will radiate away their heat, fading through red into darkness, until they become what we might call black dwarfs. They will still exist as solid objects, but they will no longer shine. The galaxy will slowly transform into an enormous swarm of invisible cinders, neutron stars, and black holes. When only these remnants remain, Milky will already be entering the next chapter, the age of black holes. Gravity will continue its quiet work, drawing stellar remnants into ever more complex dances. Close encounters between black holes and compact stars can fling some objects out of the galaxy entirely, sending them drifting alone into the larger cosmic dark. Others will spiral inward, merging to form even more massive black holes. The central giant will grow as well, slowly swallowing stars, gas, and smaller black holes that wander too close, on timescales so vast that human language struggles to grasp them. Even black holes are not immortal. According to quantum theory, they slowly leak energy through Hawking radiation, losing mass bit by bit. For a stellar mass black hole, this process takes an unimaginably long time, far longer than the current age of the universe. For the titans at the centers of galaxies, the evaporation time stretches to astonishing exponents, numbers with more zeros than we can comfortably write down. Yet, given enough time, even these will finally fade. When the last black hole has released its last whisper of radiation, a new and final era begins. The dark era. In that future, there are no shining stars, no glowing nebulae, no visible galaxies in the way we understand them now. Only cold remnants, faint particles, and the stretched-out echo of all the light that once was. The universe continues to expand, and its remaining energy thins and cools toward a quiet equilibrium. In such a picture, Milky Way itself is only a temporary arrangement. First, a luminous sphere of merged spirals, then a redder, quieter city of long-lived stars, then a dim cloud of cooling embers and black holes. Each stage feels permanent to whatever beings might live within it. Yet from the viewpoint of cosmic time, it is just one more step in a long descent from fire to ash. For us, listening now in the brief brightness of the stelliferous era, there is a strange peace in this knowledge. Our galaxy will not simply vanish in a single cataclysmic night. It will exhale slowly through billions upon billions of years, changing form as gracefully as a cloud reshaping itself in the wind. The Milky Way will become Milkomeda. Milkomeda will become a graveyard of stars, and even that graveyard will one day surrender its mass back to the fabric of space itself. And yet, in this long fading, there is also a kind of tenderness. The atoms in our bodies were born in earlier generations of stars, thrown into space by supernovae, gathered into new clouds, new worlds. Those same atoms may one day rest in the cooled crust of a black dwarf or circle silently inside a distant black hole. The universe that will someday grow dark is the same universe that once lit us into being. When we imagine Milkomeda as a smooth sphere without arms, glowing softly with ancient red suns, we are really imagining the future shape of our own story. A story that moves from youth to maturity to old age, from spirals of bright creation to a slow contemplative dimming. Perhaps that is why thinking about these far futures feels both melancholic and strangely calming, like watching the last colors of sunset fade while knowing that another day once rose before it. If you close your eyes for a moment and breathe with the rhythm of that vast timeline, you may feel something gentle settle over the mind. The anxieties of a single human day grow small next to the knowledge that galaxies themselves are passing gestures, brief arrangements of light, in a universe that will one day fall almost completely silent. And yet in this instant, in this fragile window when the stars still burn brightly and the Milky Way still wears its spiral arms, we are here to notice, to ask what Milkomeda will look like, to trace the destiny of red dwarfs, to follow the story all the way into the dark. Perhaps that ability to witness is our small answer to the vastness ahead. We cannot stop the galaxy from changing, cannot hold back the long slide from starfire to shadow. But we can understand it, tell it, and for a little while share the quiet wonder of knowing where our cosmic home is going. In the deep future, long after the Milky Way has stopped being the soft river of light we know, the night sky will be ruled by a single enormous shape, a quiet giant called Milkomeda. No sweeping spiral arms, no bright bar cutting across the center, only a vast, almost spherical cloud of ancient stars glowing like the last embers in a cosmic fireplace. Our familiar galaxy will not disappear in an explosion. It will fade into this new being, until the name Milky Way becomes just a memory in old star maps, a story that astronomers tell each other in the long evenings of the universe. Milkomeda will not have the sharp architecture that spiral galaxies flaunt. It will look more like a luminous fog suspended in the dark, thicker toward the center, thinning gently as you drift outward. If a future observer stands on some distant world within that fused galaxy, they will not see a silver band stretching from horizon to horizon the way we do now. Instead, their sky will be evenly dusted, with stars in every direction, like being inside a snow globe of light. The scars of the merger, great shells and ripples of stars, may still linger as faint patterns, delicate rings and arcs that betray the violent history behind the calm. For them, Andromeda will not be a separate island in the sky, and the Milky Way will not be a home galaxy with an outside neighbor. There will only be Milkomeda. The stories of two spiral galaxies gliding together across billions of years will sound almost mythical, like we speak today of the birth of the first stars. Our era, with its clear view of the universe full of galaxies, will feel like a brief dawn when the cosmic horizon was still generous, before distance and dark energy pulled everything else out of reach. But even Milkomeda is not a final destination, only a way station on an even longer road of stellar evolution. In the first tens of billions of years after the merger, the new galaxy will still host many kinds of stars, some blue and fierce, many like our sun, and a countless number of small red stars glowing softly. Gradually, though, the balance will shift, because the universe is patient, and patience always favors the slow and efficient. Massive stars live fast and die young. They burn like bonfires, bright but brief. Suns like ours last longer, 10 billion years or so, respectable by human standards, but still finite on the scale of eternity. Red dwarfs are different. They are the quiet monks of the cosmos. Small, cool, and incredibly thrifty with their fuel. While a blue giant might blaze for a few million years, a modest red dwarf can shine for trillions, outliving spiral arms, galaxy mergers, even the memory of where it was born. As time flows from 10 to 20 to 50 to 100 billion years, these red dwarfs will come to dominate Milky. The bright, familiar kinds of stars will gradually exhaust their fuel, shedding envelopes of gas and leaving behind white dwarfs, neutron stars, and black holes. The galaxy will keep its mass, but not its light. Seen from within, the sky will grow subtly dimmer, shade by shade, generation by generation, until only the patient crimson of red dwarfs defines what a star is to any remaining eyes. Imagine a civilization that rises during this era, long after ours has faded. For them, the word star might mean something very different. Not a golden disk like our sun, but a small, deep red ember hanging in a thick field of darkness. Their astronomy textbooks would describe a universe already grown old, where bright blue beacons are legends, and spiral galaxies exist only as reconstructed fossils in simulations. They would discover, perhaps with wonder, that once the sky blazed with more light than they can now imagine, and that Milky was once merely one actor among billions on the cosmic stage. Slowly, even these sturdy red dwarfs must surrender. The hydrogen in their cores will eventually run low, fusion will falter, and their gentle glow will fade into the pale embers of white dwarfs. The galaxy will become a mausoleum of stellar remnants, packed not with living suns but with the corpses of stars that once lit up worlds, a silent archive of thermonuclear history. Light will still exist, but it will be thin, scattered, a whisper compared to the orchestra of earlier ages. From here, the story widens again, because Milky is not separate from the fate of the universe. It is only one note in a much longer composition. Cosmologists sometimes divide that composition into eras, like movements in a symphony. And we, right now, live in the stellar era. This is the age when stars are plentiful, when galaxies still form new suns from great reservoirs of gas, when night skies are busy with light. It began not long after the Big Bang, when the first stars kindled out of primordial darkness, and it will end when the last red dwarf finally flickers out. Beyond that lies the era of decline, when almost no new stars are born, and the ones that remain are old, faint, and widely spaced. Galaxies like Milky will still exist, but they will be places of memory rather than creation, full of white dwarfs slowly cooling, neutron stars spinning down, black holes orbiting in silent majesty. Energy will still flow, but it will be like the last warmth from coals long after the firewood is gone. In the next movement, black holes take center stage. Over inconceivably long periods, they will swallow what remains around them, occasionally tearing apart an unlucky star or dwarf and flaring briefly in one last show of violence. Milky itself, or whatever is left of it, may eventually be reduced to a scattering of remnants orbiting a few great black holes, which slowly merge into one even larger dark heart. If any consciousness is still present in this epoch, it will live in a universe where light is rare, where gravity and quantum whispers in the dark define reality. Yet even black holes are not eternal. According to our best theories, they leak away through Hawking radiation, bleeding energy into space at a rate so slow it makes everything else we have spoken of seem abrupt. Over timescales with more zeros than we can comfortably write, those black holes themselves will evaporate, shrinking until they vanish in a final faint flash. When that happens, the universe enters its last and quietest era, the darkness after the last note. In that ultimate age, there are no stars, no bright galaxies, only a diffuse sea of particles and low-energy radiation spreading ever thinner as space continues to expand. Temperature creeps closer and closer to absolute zero, and structure becomes a memory etched only in the laws of physics themselves. The grand tapestries of Milky, of the local group, of all the galactic cities we know today, will have dissolved into anonymity. It sounds bleak at first, this long fade from spirals and supernovas into a thin, dark quiet. Yet there is a strange peace in it too, a kind of cosmic meditation. The universe is not being punished. It is simply following the logic of its own laws, allowing energy to spread, letting gradients flatten, moving from the wild creativity of its youth to the stillness of old age. Every bright moment, every star, every galaxy, every life that ever looks up at a sky is a brief pattern in that journey. For us, listening now in a small corner of the Milky Way before the merger even begins, this distant future is not a threat. It is a perspective. It reminds us that the galaxy we love is temporary, that the spirals we photograph and the constellations we name are moments, not monuments. And yet, within those moments, we are free to wonder, to learn, to tell stories about the shape of Milky and the fate of the stars. Perhaps the real gift of imagining this future is not to know how everything ends, but to feel more deeply how extraordinary it is that we are here at all, in a universe still full of light, able to trace the road ahead from bright spirals to silent darkness. And as we follow that road in our minds, drifting with a calm voice through billions and trillions of years, we can gently return to a simple question that started it all. If one night your descendants stand under the sky of Milky, what will they see, and what will they remember of us?